I haven't done a mistake in probably 10 years. But it happens. When I taught with EBON, I make all the exams when we taught together. Sometimes I'll give him the exam correct and he'll make the mistake. But I always had a chance to review it. So the two of us, we never made mistakes because there are two of us, one checking the other one out. Maybe I need a good student, check me out here.
Okay.
I volunteer.
I got you.
Volunteer. Metal, oxide, semiconductor, field effect transistors. So metal oxide semiconductor, that's field means electric field, effect, field effect, transistor. Right away, you expect this device to be a function of voltage rather than current. Okay, field effect. Now, before we go there, let's think a little bit, and then we move on. Suppose you have P right there, material, and you have SiO2, dielectric, and you put
Silicon
metal here,
dioxide?
say metal, I don't know. And I put a voltage source here. Okay, and this is PN, P-type. I put a voltage source. What happens on this plate of a capacitor? This is a capacitor, right?
Yes.
This is P-type, and right here there's a connection. Say I ground this connection. All right? What happens on this plate? If I put positive voltage there, you get positive accumulation of charge here, right? What do you get on this side?
Negative.
Where does the negative come from? No, this is P-type.
From the P. The
Where does the negative
phosphorus.
come from?
Phosphorus ions?
Huh?
The phosphorus ions?
What we said that when we talked about P-junction. What's P-type mean? 10 to the 17 to the 10 to the 18 per cubic centimeter, right? But there is how many? This is P. If that's the case, what's N?
One to, yeah.
10 to the 6, 1 in a million, right? So although this is P, there are electrons there.
Of course.
1 in a million. What happens to these wandering electrons? They accumulate right there. This is function of a capacitor, right? Now, here is the invention of the new device. I put a bucket in here of N and N. Actually, it's N plus N plus. All right? Now, I take this side to say, I ground it. All right? Now, I take this side, I apply a voltage to it. All right? Now, if I don't do anything here, what do we have? This is grounded, this has a positive voltage, nothing happens, right? Now, crank up this voltage, what happens here?
Generate negative.
You get negative charge accumulating in here. Essentially, what do you have?
Conductor.
A highway between this bucket to that bucket. Now they're making a connection. Now, as you crank this up, what happens? This electron, and this is positive, sees a potential, the field, so the electron goes, right?
Yes.
All right, now,
Generates heat.
which way the direction of this current,
Drain to source.
right? It's the opposite direction of the electrons. So, this is called a MOSFET. 1, 2, 3, 4 terminals. Okay? What should we call this terminal right there? Remember, this terminal determines how many electrons in here, right? A gate. Like opening the gate, closing the gate. So this is the gate. All right? Electrons come out of this bucket and go to there. What should we call that one?
Source.
Source. That's where the electrons come out of. Source. This?
Drain.
Drain. How about that?
Ground.
Is it the
Not
other
that.
gate, the back gate?
Back gate.
Heat sink.
Okay.
Here it is.
Let me show you why this is very important, especially in amplifier design, IC design. Does the back gate affect how many electrons in here? Yes, it does.
Yeah.
If I put a positive potential here, I push these electrons further out, right? I could make more accumulation here. If I put zero, one thing, if I put a negative voltage, if I put a negative voltage, it pushes them in. Put a positive voltage, it drags them down, and this is dragging them up. So this has an effect on this. This is called the channel. This is the channel. Now, channel is defined at a certain voltage. You apply voltages right away, there will be electrons here. But minimal amount till you reach a certain voltage, which is called the threshold voltage. If this is 10 to the 19 per cubic centimeter P, this was 10 to the 19. If this becomes N equal 10 to the 19 per cubic centimeter, V gate, this voltage, is what we call reach the threshold voltage. That's how it's defined, the threshold voltage. That means I go from 10 to the 19 P to 10 to the 19 N in the channel. It's called total conversion. I convert it from P to N. That defines the threshold voltage. Look, the source is ground, so we put S, reference to ground, right? So this would be V drain S. Okay? Now the current here will be which direction? PMOS, like PNP and PN. Okay, this is how the device operates. Now in your class, the back gate is tied to the source, not the ground, to the source. If the source is grounded, the back gate is grounded, the mathematics becomes very simple. All right, and that's what we try to do as much as we can. But in IC operational amplifier, you cannot do that all the time. All right, so we eliminate, yes.
So where else can the back gate be connected to besides the source?
It will be floating at a certain voltage.
You cannot
Which-
put in the other ground.
Huh?
You cannot put in the other ground with the DDS. You cannot connect it to the other ground.
Ground is ground.
Yeah.
This ground is the same as this ground.
So it's the same thing.
No, ground is ground, okay? I'm saying it could be floating. Okay? Normally I will show you, but this is beyond this course. There's a p-n junction here, right?
Yes.
Right? p-n junction. So there's a diode here. Right? The back gate normally is tied to the lowest potential. Why?
So you get the
Suppose
most
you're operating plus or minus 5 volts. Where do you put the back gate at?
the end,
Huh?
lowest part.
Why? Why?
So you get the most area, so you have the highest.
You never want this diode to come on. Right? If it comes on, there's a diode here too. You shorted the device. It's called latch up. This is called latch up in digital. So the diode, you guarantee this diode to be off by making this voltage the lowest potential. If it's plus or minus 5 volt, you put this, you tie this to minus 5. Okay? But the threshold voltage, this voltage, is function of the back gate. But the fact what actually the VT is equal to VT0, this one, times the square root is 2 is V back gate to source to back gate was 2 phi f minus the square root of 2 phi f. If source to back gate, this is, I'm jumping the gun, okay? If this is 0, you could see that VT equal to V times gamma. Yeah,
That 0 is 2
that would be,
phi
there's a
minus
1
2 phi.
times this number, okay. 1 plus.
Did we talk about gamma for BGTs? Did we talk about gamma for BGTs?
Yeah, that, I think it's that way, but that's beyond the point. But when this becomes 0, this minus that goes to 0, so VT0 equal to VT. But we're not talking about it here. You will see it in electronic 3, which no longer they teach it the way it should be taught.
Oh.
They eliminated, I used to teach electronic 3 now. Hallman teaching it, he threw away all the IC design stuff out. He teaches us whatever. 4 and 3 the same.
Oh yeah, I've heard that.
Anyway, you understand this? Now we have to calculate a current equation. Okay, the current, I'm going to tell you the results, then I'll show you how to calculate it. We're trying to say I drain to source is going to take some constant, Kn, it's going to come out to be VGS minus VT squared for 1, and it's going to be Kn VDS those two equations, but I'll show you where we're going to be working with. Kn is equal to another 1/2 mu C ox W over L. Those don't make any sense to you so right now. But where we're going, watch this. The current, the current is function of voltage. Okay? Before was IC equal beta IB. Now IB is function of square of a voltage, which makes the equations more complicated. Okay, that's just a square of voltage. Another thing that is extremely important in difference is this. W over L. W, if you look at this device, W is in the board. It has a width associated with it, right? Like this. This is W, and from here to here is L, channel length. That's the first time you encounter that the current is function of the dimensions of the device, and it's called W over L, is called aspect ratio. Well, that makes sense. I'll tell you why it makes sense. Now, if you think that the electron going this way, right? If you make the channel shorter, right? You expect the current to go bigger because the electron don't have to go very long, right?
It's just like 2 LEDs.
If you make the channel wider, in other words, that wide, here's the channel, and it's got to go to there. You make it shorter, the electron don't have to travel that far to get there, so that increases the current opportunities, and you got the width of the channel is like the table. Think of the channel from here to there. This is the width. You make this shorter, this shorter, more electrons going to get there. You make this wider, you're increasing the cross area for the electrons to go, so you get more current. that is there. So that is important because in bipolar, the dimension of the device didn't come into any equations. Now here it comes in equation. Steve, you're sleepy, or you've slept last 2 or 3 days? You haven't, huh? Or you have lunch, pizza, I ate pizza for lunch
Yummy.
from Panera.
Oh.
How was it?
You love that small pizza? Now, let's see how this device operates. Here we go. VDS, and here's IDS. Okay? Now, let's argue ourselves how this device operates, and then we'll see. If you somehow you apply a gate to source voltage, that you have a channel now. Okay? Now, if you got a channel, now you start pumping this voltage. As you pump this voltage, and all of a sudden something happens. Look what happens. Remember, this is a PN, right? What is there here?
Oh wow.
What's this? What is this?
P.
Depletion region, right? PN, this is the diode. Depletion region, correct? Now, if I increase this voltage, what am I doing? Forward bias or reverse bias? I'm increasing the voltage on the end.
So it's more negative.
More negative, reverse bias. What happens to the depletion region?
Decreases. It
Goes narrower or
Narrower.
down. Narrower.
no?
Really?
Because you're.
It goes wider.
Why? These electrons are going.
PN. If you put this as positive, it goes like this, right? If it goes negative, if you put this as negative, and eventually more negative, it'll hit here and it will be breakdown. So this is getting wider. What happens? This wider depletion region pushes against the channel, like this. And it pinches it off. Then you go more VDS, it pinches it off. Now there's no channel connection from one end to the other. What happens to that curve? Huh?
It's like,
Clip? What does that mean?
you're not stop increasing.
It doesn't go to zero? No channel. I open the switch. Huh?
No current.
It's gonna flatten.
No current?
But
It'll flatten.
It goes like this?
No.
but if it does that, then it's going to bounce back, is it not?
No, but it doesn't do that.
It's gonna
Let me
flatten.
show you why it doesn't do that. There's no channel here. Say you have R, switch, you ground here, and you put 5 volt here. Where's the 5 volt go?
The switch is open, nowhere.
No, I mean, where is the 5 volt now? The switch is closed.
The switches are closed. The resistor.
Right there, right? The voltage goes here. Now, open the switch. Where's the voltage go?
Stays.
How much current will be here?
Zero.
So where's the 5 volt?
On both sides.
Where is the switch?
Yep.
Right?
Yes.
That's here. Let's put 5 volt here. Where's the 5 volt gonna go?
On the edges.
On the open part of the circuit, right?
That's right.
This is positive potential. He's an electron, sees a positive potential across of it. What does it do? it tunnels through. Right? Now I increase that voltage to 6 volt, here's the channel. It remains tunneling because I increased this. So what happens to the current? It levels off.
Yeah, level something was flat.
It looks like that. Okay, it's leveling off. Now, this is for VGS1. For one channel, if I put another VGS, I'll get,
Nice.
does this look familiar?
Yeah.
All right. Where do they go? Where do they go? VA, early voltage, right? But we don't call it VA. We call it 1 over lambda, or lambda.
Oh.
Lambda is equal 1 over VA. In other words, the units of lambda is called 1 over volt. Lambda is AS.
I was gonna ask you, could you
Huh?
go backwards and explain the reverse bias thing that you were pointing the arrow from the source thing?
Here,
Yeah, right there, right there.
there's a diode here. Right?
Yeah.
Diode.
Oh, okay.
I'll put this is more positive than this. This is ground. Right?
Oh, yeah.
And the depletion region widens in the diode. Right there. Pushes here. All right, so this is VA. This is VA. What's the slope of this? This is, you probably missed. 1 over R out, right? Right?
Yeah.
The slope of that line is 1 over R out. Now, what's the region is this in bipolar? What is this in bipolar?
Saturation and linear. Yeah.
Sat and linear. In MOSFET, this is linear, this is sat. Look at it. This is linear. And this is saturation. So where do we build amplifiers? In the saturation region, right? Because you put load line on top of that, you want it to intersect here. Not here, here is a big variable, the current. Right here, look, if the Q point going up and down like that on the load line, how much current changing? Very little. So we build amplifier in saturation region. Now we have to define how is saturation region, what is the linear region, equation-wise, mathematical. But you understand how this device works now. This is called enhancement mode MOSFET. That means there's no channel when you buy it. There's what another MOSFET called depletion mode MOSFET, where the channel is there and you cut it off by applying different potentially. But that, instead of positive, you apply negative and you push the electrons away and you work with it. Depletion mode MOSFET are normally used as resistors, active load resistors. Enhancement mode are for amplification because they're better devices. All right. Now let's see if we can calculate this, the current equation that I had put up here. What's the units of current? Ampere? Not right.
Joules per second.
Oh, coulombs per second.
Coulombs per second.
Right. What's the unit of current?
Coulombs per second.
Coulomb, basic unit. It's always you have to go to charge, time, and space, right? So the unit of current, I, is Q over time, right? That's the basic. Before I go there, Let's take a look here. Device notation is this. This is N channel, and I'll write next to it P channel. You see it as a 3-terminal device or 4-terminal device. Gate, drain, source. The arrow always on the source. Okay? You can see the current. What's this current? 0. It's capacitor. The current comes straight from drain to source. The electrons go up from source to drain, right? Now, that doesn't show the back gate. When you see that notation, it assumes the back gate is tied to the source.
Okay.
All right? But then sometimes you see it like this. Four-terminal device, this is the same. Drain, source, gate, and there is back gate. But now there's an arrow on the back gate. Which way the arrow should go? Logical. Up. In other words, this way or that way?
That's it.
Why? The notation, they worked very hard on this notation when they designed them. It's the other way. Let me show you why it's the other way. This is N channel, right? N channel. This is P, N. Right? It's from P to N. Like, we go back to diodes, okay?
Yeah.
So this is N channel. P channel. Source, drain, gate. Current going that way. Source to drain, it says the drain to source. This is gate, and this is still 0 current going this or out. And this notation would be, there's a back gate. Gate.
That's a D.
And direction from current is this way. Okay? Again, the arrow from P to N. Okay. Let's derive the equations. Now, if that is the current, this is the charged IDS. It's going to be charged, induced in the channel, divided by time, transient time. Transient time from source to drain, in other words, source to drain. Okay, and that is Q, is written as Q over tau. Tau, since it's transient time, is channel length over the velocity of the electrons, average velocity the electron has to travel. So, and this will be written as, the channel length is L, average velocity mu
Probability.
E. That comes from electron velocity from E and M, you know.
Yeah.
What's mu?
Permeability.
Mobility. Mobility times the electric field, it gives you the velocity of the electron. Okay? It's extremely hot in here.
Yes.
Yeah.
I'm wearing a sweater, I'm starting to sweat.
No AC.
All right, now let me ask you this. When we talk about N channel and P channel, we have mu N and mu P. I haven't put the subscript because they are two different devices. Which one has a higher mobility? Electrons or holes? From logic, not
Electrons.
E and M, just logic.
Electrons.
Why?
They can move. They have less mass.
Huh?
They can be shaded.
They have less mass.
Remember, this is movement in solid, not in vacuum.
Exactly. The whole time.
I was just assuming basically.
Okay? Movement in solid, not in vacuum. Which one moves? Okay, which one has a bigger mass than the other?
The whole.
The hole. So the hole is fatter than the electrons, right?
Yes.
So it should move slower than the electron.
Yes.
So mobility of the electron is larger than the hole. What else affects mobility? I told you one, mass. What else affects mobility?
Energy.
Energy,
Charge density.
temperature. Why temperature?
Because that's the average
The
movement speed.
more heat, the more collision.
That's the speed.
That is a perfect answer. The big guy. More heat, more collisions. If you raise the temperature here, and we all want to get out of this room, start pushing each other to get out. None of us will get out, you know, because we start colliding with each other. More heat, more scattering. It's called scattering, collision. What else affects it?
Pressure?
No, we're talking about solids.
Oh, yeah, okay, yeah, that's biology.
How crowded it is. We're talking about minority charge, electrons in a P. How many, so it's function of doping density. The higher the doping density, the slower the velocity, the lower the mobility.
More electrons.
So those are three elements that, in other words, if you want to look at mobility as an equation, and you're not a physicist yet, you should have mass in the denominator, temperature in the denominator, right? And what I said, the other one, doping in the denominator. That all reduces mobility.
Is doping like concentration of non-electrons?
Yeah, concentration electrons in the, you know, how crowded.
Silicon dioxide.
You could move a lot faster if there's only you in the highway, right?
Oh, yeah. Okay, makes sense.
All right.
Yeah, the biologist comes in. Wow.
Now, if you look at tau then, continue with this. I'm gonna write it as L over mu, and this will be L minus L VSD. Remember, electric field is volt per distance, right? Source to drain, because that's the field that we applied, which will be L squared over mu V ds. I reversed this and got rid of the minus. That's tau. Now, charge Q is equal the gate capacitance per unit area, this is a capacitor we're starting about, times the V excess voltage in the channel. This we will talk about. This is the one you need to comprehend. What is the excess voltage? All right. We apply VGS. Okay, it's applied in the channel. Then we reach threshold. So the remnant of the voltage, because threshold opposes VGS, the remnant of that will be VGS minus VT. That's the excess voltage, the difference between the two voltages. Then we come in and apply VDS across it, right? Suppose there's a linear distribution of that VDS across the channel. So the average voltage in the channel is VDS over 2. Right? One is 0, one is VDS. So the excess voltage right there is actually VGS minus VT minus VDS over 2. That's the excess. This is one voltage that we establishing the channel, and this one is the voltage distributed across the channel from the source outside.
Because after you halfway,
Now.
you know?
I think this is when it's already built.
Yeah, so it's open, so if it's already got the potential to get halfway, it's not to continue.
Doing this, plugging everything
I
in,
think that's just the average distribution of
okay?
over the channel.
Oh,
You get this now. You just go back and plug it in. IDQ over tau, put C gate. And I'll tell you what C gate is. I'm burning out.
do you want to open the door?
Yeah, please. So, the gate, C gate, this is the capacitance, and we know that is epsilon A
Open these two rooms. And
over
they adjusted it
D.
for heat map.
D is thickness of the oxide.
But it's only these two rooms that are affected.
Of, this is W over L, W times L. That's the area. Okay? And you put all that stuff, you're gonna end up with the IDS. What's this? IDS is equal mu epsilon over D W, this is what you end up with, W over L, VDS okay, times VGS minus VT minus VDS over 2. And this will be written as mu C ox. This will be written as mu C ox. Oxide capacitance, where C ox equal epsilon over, or is equal to CG over A. Just capacitor per area. That's the equation. And that equation assumes something. This equation is good only, you hear what it is good for. VDS less or equal to VGS minus VT. This is a linear equation. That's the linear region. That's in here. This region is VDS less or equal to VGS minus VT. That means we haven't formed the channel completely. The minute you form the channel, you end up here. Now you have the channel. And at this point, VDS greater or equal to VGS minus VT. So at the point between them, this is the equal sign. If you put, if VDS equal VGS minus VT, that means you have channel already formed. Put in this equation right there. You're going to get IDS is equal mu Cox W over L VGS minus VT squared. So this equation is good for the equal sign and greater, like this. Or sometimes you see it, we drain the gate greater or minus VT. That's the same equation. This is saturation region. And this is where we build amplifiers. Voltage control resistance. Okay. So that, where are we going? What else is left? Pi and T model, right? We're gonna spend a lot of time working problems with this, okay? Sometimes, see, I put this to be Kn. Kn, sometimes they call it beta, but not the same beta. Sometimes they call it little kn or kn prime. But to make it easy for you, I'll give you the equation on the test. And I'll give you the variable so that we don't confuse ourselves. Okay.
Don't forget, otherwise you'll give us another grade point.
I'm not making that mistake again. I'll show it the E-bond to check it out before.
That sounds good.
Okay, but that's okay. Happy Thanksgiving. I wrote you that.
Yes, yes.
I was gonna say Merry Christmas and Donald told me no Thanksgiving before Christmas.
Yeah, I'm still waiting on my Christmas present, but you can give me that November 14th, I'll take it then.
Okay. It's in the write-up, how you derive, I'm not gonna derive it here, how to derive the pi model. Here's the gate, here's the drain, and here is the source. From there to there, you'll find out G7 VGS. Here's R out. What was the value of R out? VA over ICQ, right? We ignored them. No, I'm not going to ignore them on the test. It was VA over ICQ, which is really 1 over lambda ICQ or IDQ. Because 1 over lambda is equal to VA. I told you that there, right? This is R out. Here's VGS. What goes here? R pi. What's the value of R pi in a MOSFET? What's the input of the MOSFET?
Positive. VGS.
The MOSFET. What's the input? There's a resistance. It's a capacitor. It's open circuit,
Exactly.
right?
So it doesn't exist.
right? Look at the current source. G sub M, VGS, here's VGS. It's a current source, voltage dependent current source. And bipolar was current dependent, beta IB and IB was coming here. There's no R pi. If we're gonna go to T model, this stays G sub M VGS. This is the source. Here's the drain. And here's the gate. This current always 0. No current in the gate. What's this? What do we call it in the other one? T model, huh?
It was an RE in the other.
Little RE, right? 1 over G sub M. That's a T model. With this stipulation, 0 current. Now, if the current IDS equal to K VGS minus VT squared, you want to calculate G sub M? Here you go. The IDS, the VGS. Take the derivative of this. Come out to be 2K VGS minus VT. Right? So there's G sub M. And a lot of time they write it differently. 2K, this can be written as the square root IDS over K. And you bring K in, it'll be 2 square root of K IDS. You see a lot of forms, I don't remember them. All I know how to derive this, and the other forms are there. This is a T and pi model. From here on, we gotta get the concepts hammered in using examples. Okay? I think here's a T model. There is a table in section 5.5, and there's a summary there. The only thing difference between P channel and N channel is KN, KP, and VSD instead of VDS, ISD in terms of IDS. That's the only, all you have to do is reverse the currents and the voltages. Okay? Sounds like too much right now, but we will get it. Okay, that's enough for today. Did you ever notice that problem number 3 is the same as problem number 2? The pi model?
Without V.
You notice that?
Without a V, any?
I put the V in I put the V in the right way.
Yeah, I thought it was the same too, I'm sorry.
It is the same, except I changed the little numbers
I
off,
saw the source, it threw me off.
but I put VN in there. I did this on purpose, but I screwed it up, okay? I wanted you to see if you could draw the small signal model and calculate the gain. But if you didn't know how to draw the small signal model correctly, I gave it to you and calculate the gain. So I want to differentiate what you know. I screwed up.
I thought you were tricking and thinking.
No,
that it
I'm
was
not
like a
tricking you. That
differential,
was
like a-
stupid.
Like a conceptual problem, like, oh, gotcha.
Yeah.
You didn't know it was in there.
I don't know why the TA didn't call me. I mean, maybe a poor man, he called.
I thought it was gotcha thing.
No, if he called, no, I don't know.
We don't
He
know.
may have called and I didn't answer.
No.
Although I was
He
waiting for
didn't
him, I
call.
should put him in my contact so his name will come out.
So there's a quiz on Thursday?
Not this Thursday, no.
Not this Thursday, no.
Wait,
We don't have quiz for 2 weeks. Then after we get back
This
from,
Thursday, is demonstrating the.
Oh, this Thursday, yeah, that's that much I see.
yeah, because next Thursday is a holiday, right?
Yeah.
So the following Thursday, we will have a quiz, and the
Yeah, I'm gonna do
following
Wednesday.
Thursday, we'll
That's
have
fine,
quiz.
that
and
one.
I was gonna be like, okay, I can go.
No, we don't have to go to
The
rotation,
last
right?
Thursday of class will be quiz.
I can't go on Wednesday.
On Thursday? No reason.
There is, they sent you email.